basically compact closed categories. Instantiated to finite dimensional vector spaces, to formalize something that's called the generalized quantifier theory of natural language. And natural language is human language, is what we see. I have been working on this for quite a while now, for about 2-3 years. First with unvary project here, where we really worked hard with Frobenius algebras, but then got really nice diagrams and could go some miles with it, but we couldn't prove the main results of this current work, which is soundness and completeness of the relational instantiation of the category theory to the true theoretic semantics of generalized quantifier theory. We can prove that with Frobenius algebras, and then I corrupted Jules, which at the time was in Queen Mary, now in Oxford, and then he suggested to work with Bialgebras, which made the whole thing work, basically. So this is a short paper, and the long version is submitted to a journal, but it's on the archive. Okay, so just to give you an idea of what's happening, so we are working in this paper on what is called, more generally, computational linguistics or natural language processing. And these are subfields of AI, or artificial intelligence. And the goal of people who work in these areas is to sort of make computers understand human language. So they may be able to communicate with us similar to the ways we communicate with each other. And people who are more mathematically minded in these fields, they say, well, human language is very vague, it's almost a miracle we understand each other, well, mathematics and logic is very precise, and why don't we try to translate language somehow into logic and math to make it precise? And one of the first sort of masters of this translation was Montague, a student of Tarski, in fact, whose thesis was on infinite dimensional axiomalizations of ZFC. He later got interested into formulas in natural language, and he presented a mechanical translation of natural language into first-order logic. So, for example, you have a sentence like cats sneeze. This translation will be turned into this first-order logic formula, which we all know and love, and there is no question what the meaning of this is given a model. On the contrary, Chomsky came up later, and he wasn't interested in first-order logic per se, but he was interested in rules, and he said we can in fact take the grammar of natural language here and formalize it using a set of generative rules like so. So for example, we can say that a sentence, in no matter what language, for example, is generated by a noun phrase followed by a verb phrase, where my noun phrase can be something like cats and dogs. A verb phrase is generated by a verb followed by a noun phrase, where the verb phrase can be something like sneeze or sleep, and a verb itself can be something like love, admire, kiss, give on, etc., etc. So then if you're given a sentence like cats sneeze, then what you can do is you can sort of formalize the grammatical structure of it. You can well, it's a sentence, it has a noun phrase cats, and it has a verb phrase sneeze. So it follows by subsequent applications of these rules. That's what you get here. So if you are a follower of Montague or Chomsky, now you stop here and you say, well, we have formalized natural language in one way or other, or even in two ways. And now, can now computers, given that these are all implementable, can they do what humans can do with language? And let's then experiment. So can you guys guess what is this missing word? So I've put a red block on one word, and it's the same word all over. Same word here, same word here, same word here. And I want to see if you can guess what this word is. Is it visible? Vampire, somebody said? Vampire, yes. Well, maybe that was an accident. What is this one? It is actually visible. Butterfly. So these are basically the first paragraphs of Wikipedia entries of bumper and butterfly. And did you use Montague's approach or Chomsky's approach? So the thing is that Montague or Chomsky's methods cannot solve these things, but we can. And then the question is, so what are we doing? So the closest this gets to is something is called the pragmatic or distributional semantics of natural language. So the top, if you remember, is compositional distributional semantics. So that's a distributional part, and it came from ideas of Firth and Harris, who was a supervisor of Chomsky. And they argued differently. They said meaning of a word depends on how it's used. That's the pragmatic. And words that have similar meanings often, it's the case for them that they often occur in the same context. That's the distributional. So we have been actually looking for formalizations of this approach. So these are intuitions behind the approach. They're very tangible. You relate to them, but how are they formalized? And the earliest I could find was work of Rubinstein and Goodenough from Berkeley in 1965, where they take a corpus of text. They basically implement this model using vectors as follows. They take a corpus of text, they fix a set of context and target words, and then they build something which they call a co-occurrence matrix or context matrix with rows and columns labeled by these context words and these target words, and where the entries of the matrix are degrees of co-occurrence of target word with the context word. And co-occurrence can have different meanings. It can be like just occurring in a proximity window or in a certain grammatical relation or something else, and these degrees are obtained by recording co-occurrences within a sliding window which spans the whole corpus. Alright? So then you have your matrix, and then you can take rows of the matrix which become vectors as meanings of your target words, right? So that's how you get your vector. You are applying something which probably you did when you gave answers to this. You look at the context, you count co-occurrences, you build your matrix, and each word gets a vector representation as a result thereof. So here's an example. So we have the dolphins occurred 500 times close to fish, only 10 close to horse, 700 close to pet, and never to blood. So then we get this vector representation, this row, as the representation of the word dolphin. These are the target words, these are the context words. And then once you have your vectors, you're in the realm of linear algebra, and you can do really nice things. A prominent operation is taking the cosine of the vector of the target word, and using that to represent the degree of similarity between meanings of this word. As you can see here, dolphin and shark will have high degree of similarity, whereas dolphin and pony won't. Okay, so then came along this compositional distributional semantics, which aimed to reason about meanings of phrases and sentences of natural language. And it turned out that we cannot apply the distributional hypothesis anymore in this setting. For example, can you guess what is the missing sentence here? So it's not directly applicable. And indeed, people who worked in this setting, they argued, well, the meaning of a sentence doesn't really depend only on the context of the sentence. What we can say that it depends on the meaning of the words in the sentence and, of course, the grammatical structure of the sentence. But the meaning of the words can come from the distributional setting, right? So what we have been doing, which we call categorical compositional distributional semantics, starting around 2008 in Oxford, and I put this symposium on quantum interactions here because we are doing QPL. Some people ask, what's the connection to quantum? But the first paper appeared in the quantum symposium anyways. So this is how we argued. So we said, well, we have a semantics, which are vectors for words. And, of course, language has a syntax, a set of grammatical rules. And what we want is a structure-preserving passage from syntax to semantics. When we have vectors for the semantics, what can the syntax be? We have a set of grammatical rules. How can we represent it in a way in which we can get a structure-preserving passage to vectors on the semantic side? And then, since vectors, for example, vectors and linear maps, they form a compact closed category. So obviously you ask, is there a compact closed category of syntax? In which case, the structure-preserving passage between the two would be a strongly monadal functor and everything would work out really nicely. And it turned out, surprisingly, that in fact in 1999 Lambeck invented something which is called pre-group grammars, which are the partial ordered versions of compact clause categories. So these are being used to analyze syntax. I won't have time to talk about these pre-group grammars, but this trio is now called compositional, categorical compositional semantics, which you can in fact just show it in one slide. So you have category of pre-group algebras, easily definable, category of finite dimensional vector spaces, you have a strongly monoidal functor. Between the two, all you have to do is to say what it does on the basic grammatical types of these pre-group algebras, which only turn out to be two, n and s, for noun phrase and sentence. So you assign to these two basic vector spaces, capital N and capital S, and then you add to the setting what formal semantics is known as a principle of lexical substitution. That the meaning of a string of words, W1 to Wn, is f, this f, of the grammatical parts of the string alpha, so this is the category pre-group, it's a morphism in this category, alpha, applied to the tensor product, so this tensor is a category FV of the meanings of the words of this string. So you add this axiom to the set. And everything else then follows by monoidality and compositionality. Here's an example. If I want to calculate the vector meaning for red car, I take the f of its parts, which turns out to be this guy. It's epsilons of the compact clause category. Apply to the meaning of red tensor meaning of car. This will turn out to be this baby in finite-dimensional vector spaces. Red pre-group grammars make sure it has a type such that its meaning will be an element of n tensor n. Car will have a meaning which is an element of n. Here's a typical member of n tensor n, typical member of n. These will then be filled by concrete matrices and vectors that you get using distributional semantics from the corpus. And then once you calculate these, so this you can calculate easily, then you get such a closed form which will give you the meaning of red car as a vector in n. Or automatically, really, you don't have to do anything for it. Then, so the question is, how far can you push this framework? Natural language is very complex. You have relative pronouns, you have adverbs, you have prepositions. How do we apply this setting to those constituents? So, for example, in 2014, we have a paper in a conference called Manuals of Language, and then 2 journal papers afterwards. We show how you can use Frobenius algebras to reason about relative pronouns. So the meaning of man who ate cookies will then be calculated exactly in the same way as before. F of the parts of this clause, which turns out to be this diagram, this morphism, applied to the meanings of the words therein. Therefore, the meaning of the relative pronoun, we put this construction, this diagram corresponding to this morphism of the category. If you do your calculations, this is what you get at the end as the meaning of this. How many people don't know how to read this diagram? No, you know. Okay, you know, okay. Okay, so the question is then, like next step, how can you add quantifiers? There is a talk tomorrow in the workshop by Dimitri Kachaklis who will show how you can do coordination here, words like and, or. So what about quantifiers? So I was stuck here for a long time because quantifiers, you have variables around, and there's no variables in a compact clause category. You cannot do categorical logic on a compact clause space. You need something stronger. So how can we do something like this? And then I discovered if you do generalized quantifier theory of natural language a la Barwise and Cooper from 1981, you can model quantifiers in a way where you don't meet any variables at all. So this is, you start with a Chomsky grammar, so a set of generative rules, a sentence, MP followed by VP, VP, V followed by MP, where an MP is now a determiner followed by a noun phrase, a noun, and determinants are things that are quantifiers, so A sum, all, no, must be 1, and everything else is as before. So the semantics that Barwise and Cooper suggested for this setting was you have a universal reference set U, and you define this map. How If you have a rule in your generative grammar which sends MP to MP, N to N, VP to VP, then you set the meanings of these MPs, Ns, and VPs. These are the terminals of the system to be just subsets of U. If you have a rule V to V, so you have a transitive verb to V, the meaning of this terminal V will be a relation on U, a binary relation on U. That's for transitive verbs. For ditransitive verb, you'll have a ternary relation. And more importantly, for a determiner, its meaning will be a map from power set of U to power set of U. And how does that work? So for example, determiner sum applied to A is a set of subsets of U whose intersection with A is non-empty. No A is a set of subsets of U whose intersection with A is empty. So these are logical quantifiers, the first four. But you could also talk about some quantifiers which are non-logical, where most A is a set of subsets of U which contain at most elements of A, and few A contains subsets of U which contains few elements of A, where you then define most and few in your model as you wish. So no variables. So you extend this compositionally to phrases and sentences very easily. The meaning of a phrase, determiner followed by a noun, all men, some men, is just meaning of the determiner, which we defined before, applied to the meaning of noun, which we defined before. Similarly for VMP and then PVP, just apply the meaning of one to the other. When it's just a set, you treat it as a unary relation. And then for sentences, you define the truth value saying meaning of the sentence S in the generalized quantifier is true if the semantics as defined of S is non-empty. So this setting has to satisfy a set of axioms, the most important of which is called conservativity, or the living on property, which says X has to be in D applied to N if and only if the intersection of X and N is also in D of N. So one can stop here and argue what does it mean forever. You can think of it as only the part of X that is common to N matters when you are verifying the meaning of your quantifier. This is the condition that makes the following two sentences equivalent. All students snore, all students are students who snore. So that makes this equivalence possible. So then, if you want to, here's an example for the meaning of some men sneeze. You calculate the intersection of sneeze and men and check if it is in the set of sets some men. Okay, so I'm almost done for my part of the talk. So what happens so far is that you have the pre-group grammar. You took it with this functor to come back to those categories and instantiated the vector spaces to get the compositional, distributional, semantics. Then to get quantifiers, we have to start from a context-free grammar, translate it to pre-groups somehow. And then here yourself, just come back to those categories we had by Bialgebras. And then if we instantiate to rel, we get the soundness and completeness theorem with regard to the truth theoretic semantics of generalized quantifiers. To my surprise, I almost gave up, but then discovered this map, the translation between context-free grammars and pre-group grammars, exists and has a large class of literature assigned to it. So it starts from the 30s, the work of Barwise and Cooper, who translated a context-free grammar to a right Bialgebras grammar, later translated to a Lambek grammar, and finally in the 90s by Bushkovsky to a pre-group grammar. Explain, if you want, ask me later how this works, and I will tell you it's really nice and beautiful. And finally, the Bialgebra part.
How long is left?
10 minutes.
Well, we should over a little bit. But I think probably everybody here knows what Bialgebra is. I guess that if you don't, you're probably sitting next to someone who does, so just ask them. It's a monoid, so we're in our abstract setting is, like Manu said, it's a compactors category. So we have a monoid and a comonoid that satisfy some stuff, and we draw pictures of them like this. And we need to distinguish the colours because we can dualise things, so we can turn these upside down and we have to distinguish them. This is the Bialgebra law. Okay, so we needed to work with certain concrete Bialgebras. So this started when Manoush had this, basically this intuition that she drew this diagram and said, this looks like what it ought to be. And then most of the work was figuring out exactly what is the actual specific semantics of the elements in this diagram and finding the right, what we initially thought was a Frobenius algebra, but it was actually just a Bialgebra. this was the biggest part of what we had to do. So one of the key things from Manusha's part was in generalized quantifier semantics, the meaning of a determiner is a map from the power set of the universe to the double power set of the universe, which in other words, it's a relation between the power set of the universe and itself. So if you're in the category of relations, so the category is objects, the sets, and morphisms of relations, and you take an object which is of the full power set of something, you can define a certain Bialgebra which gives you the operations which you need in order to talk about generalized quantifier theory. So this is the definition of the particular Bialgebra we're using. So so the first two, these are the comonoid operations, and these are the standard ones. So this is copying and deleting. And if you dualize that, you get, well, the dual of copying and deleting, and that gives what's, I think, standard Frobenius algebra on REL. It doesn't rely on the fact that your object is a power set. But for the other operation, instead of taking the dual, we take something else. And here we do use the fact that our object is a power set. So so the monoid operation is its section, and then its unit is the universe, which is an element of the power set. So this looks reasonable. The equivalent in finite dimensional vector spaces somehow makes me and lots of other people a bit uneasy, because what you actually have is a vector space with a fixed basis, which is the power set of some set. And again, the first two, this is a standard comonoid operations which don't depend on anything. But the second two, this is a bit strange. So so to define a monoid operation on this, this should be a tensor product. So V has a fixed basis, which is the power set of U, and so a typical basis element of V tensor V has the form A tensor B for some subsets A and B of U, and so we define it like this. So this is kind of strange, but it does seem to work. Yeah. We're not exactly sure about this, but for now it's working well enough. Okay, and so, for example, this is the verification of the Bialgebra law. It just it goes through. This is some technical note, so we don't have a Frobenius algebra, so we don't have a theorem that says we can reduce everything to spiders. We have to be very careful with what rewrites we're allowed to do. Okay. So now we're working in. We're drawing string diagrams in a setting where our objects are power sets in REL or vector spaces spanned by power sets in vector spaces. These are our basic operations. We have noun phrases which output a word. Nouns output a word. This is a verb phrase which, if you give it a word on the left, it gives you a sentence. This is a verb which has a subject and an object. And then a determiner is a thing that turns a noun phrase into a noun phrase. So you give it cats and it gives you back some cats, for example. Okay, and so we can give a diagrammatic rewrite that corresponds to the conservativity property, which I guess I probably don't have time to talk through in detail. Okay, so if you have an example like all men sleep, so this is the typical thing of what happens in quantum linguistics. So we have the top half and the bottom half of our string diagram. The top half is the tensor product of the individual meanings of the word, so all men sleep. So this is the stupid thing that existed before Manouche and Bob came along and told them how to really do it, which is you compose this with something underneath which encodes the grammatical structure of the sentence, and it links all the words up in the right way. So because we're working in compact closed category, we can rewrite this into something that looks a bit more sensible, and then we can also use the conservativity property to simplify this a bit more as well. So you get, this just goes through D and these go away. And you can also, so this is an example where the quantifiers in the object position. So, okay. So, the point of this was that we wanted a soundness and completeness theorem, because if you instantiate these things in rel, for example, in rel the usual thing is that this sentence space here is just the tensor unit, which is the one element set, which means really this is an abstract scalar, so it denotes a morphism from one relation from 1 to 1, and there's exactly 2 of those which correspond to true and false. So what we want is some soundness and completeness theorem where this thing is true if and only if the sentence is true in generalized quantifier semantics. And well, you have to. Okay, so the determiner is straightforward because generalized quantifier semantics gives us a map from power set to double power set, which is the same as a relation. So there's basically no choice. For the other things, we spent quite a long time going back and forth on what these should be. Because these are both subsets of U, and equality is not the only thing that you could put. You could put one as a subset of the other, for example. And straightforward equality is the one that works for now. But I think when we continue with this, some other variants might be useful for some other things, possibly. So when you choose them this way, you do get a soundness and completeness theorem. So okay, this is what I said. So the abstract scalar is a relation between 1 and 1, and so if it relates the element to itself, then it's considered true. And so we do get this theorem, and it's essentially by brute force. We've put all of the ingredients specifically in there by making our objects being power sets. So this theorem is essentially brute force. The definitions were written to make it true. And then you can do the same thing you can do the same thing with 0 and 1 valued vectors, and essentially your proof is exactly the same. And then if you want to go beyond that into more general vectors, well, then it gets a bit mysterious because these things can be arbitrary numbers and they're going to have to come from real data. So this is, I think Manoush has done a little bit of work on that, and mostly this is for the future. So, okay, that's the stopping point, I think.
Any questions?
Might be a question for Manoush. Have you got any sense of how this is going to be implemented at all? Or can you give me anything?
Yes, we have in the next slide, also in the paper, we have some examples. So why do you think it's difficult?
I just didn't get a sense of how you'd start building these subsets out of corpus data.
Actually, I want to say it's not difficult, and this is what the corpus people do all the time.
Okay.
Because, like, for example, when we have a vector space, so you think the dimensions are singletons, right? Just one word.
Mm-hmm.
You think this is like killed. However, it's not killed. It's the lemma corresponding to kill, which is the following set. Kill, killing,
Mm-hmm.
killed, killer, kills, etc., etc. So these dimensions are already sets. So that we have subsets here is not a big deal. What is interesting is how you interpret the quantifiers on these sets. And I've got some examples here. Like, for example, if you want to, you have a set here, and sets here as features or lemmas. Then you say, okay, what is all applied to this set? So you go to a corpus and check whenever all elements of the set have feature that corresponds to this sound, meowing and pairing, to lemmas corresponding to those, or to lemmas corresponding to showing this kind of behavior, sleeping and snoring. So whenever you saw cat, it was close to sleep or snore, and whenever you saw kitten, it was close to sleep or snore, and you get a number out. Whereas for sound, it may not be one of them has this property. So these numbers increase, for example, as you can see. And once you have this, everything else then this follows compositionally. You can build a vector for all animals, you can build vector for all animals run, and then you could also do very nicely entailment between the two.
So those cats kittens sets, are they like superpositions of cats and kittens?
No.
Okay.
No, they're just cats and kittens. They're both alive as well. No, they're not superpositions. Why do you say superposition?
Well, because with the kill lemma there, you've got you're really doing some sort of you're mixing together. Well, you're doing something to all those instances of words, and it's not like you've got separate representations for each of the full kill words. You've sort of added them all together to make one lemma kill.
So if you put them in one set, that is called superposition. We put a set of things in one set.
No, maybe
No, we can discuss it.
talk about that.
One of the reviewers of the paper, which we have a guess who this is, but said you could do this using density matrices.
Oh, okay.
Because density matrices are used, and projections are used to do subsets in vector spaces. Yeah, I'd love to know how that works.
Ross.
So I didn't see in the talk where you were using the Bialgebras structure.
Yeah, Bob asked us this as well.
No, that was the anonymous referee.
I lost track. We haven't used it yet. It's Bialgebra law is.
Okay.
My view is it says that we're not just completely making it random operations, but it has some kind of mathematical sensibleness, and it will probably drop up somewhere, but it hasn't yet.
Do you think if you put it in more complex sentences, like all men who sleep also snore, then it might show up, because you have provenience in who, which might then correlate with Bialgebra.
So your white dot is the same provenience algebra you use for your generalized.
Which is the canonical one of vector spaces.
Any other?
Just a comment. It's a very different type of biology than we usually work with.
Yeah, I can see that.
So I don't really understand. I don't have no intuition for this particular one. It's very different than the ones we've been hearing here the whole week.
Yeah, because the
Use a braided one.
isn't
Huh?
grouped, right?
Use a braided one. A braided version.
Braided, what do you mean?
A braiding. You use a braiding here, not a.
This braiding.
Yeah.
This is weaker than I guess what usually comes up.
Not true?
I thought you said your category was compact.
Yeah.
So that's symmetry and everything.
Oh yeah,
It's just
yeah. I guess that's not really a braiding. This line does not need to be broken.
Oh, okay, sorry.
Yeah.
Yeah, you mentioned there's something slightly awkward about using the vector spaces because this relation you define from a tensor product of vectors
Yeah.
into a vector is a bit awkward, but I didn't understand like what's exactly the problem
Oh,
with it or why
it's
is it.
just a feeling.
Okay.
It's his gut feeling. This is what I
So
think.
do you need like more structure in this thing? Do you need it to be like
So,
more natural?
well,
or
a
intuitive?
general element of this vector space is some formal linear combination of subsets. So different subsets can have arbitrarily different coefficients. So you have subsets which are related, like one is the subset of the other, but their coefficients aren't necessarily related in any way at all.
so related question in applications typically how big is the set U?
Yeah, I also wanted to say something like that. So the vector spaces in linguistics tend to be already very big, and they have to be implemented with sparse matrices, and we just bumped it by an exponential factor. We don't need the
You
full.
might not need the whole power set.
Yeah, we realised this yesterday.
Subset of the power set.
So you need some sets which you need because your determiners need them, and then you just close it under intersection.
So like a mid-semi-lattice bounding system.
Yeah, it was just a short follow-up to the Bialgebras that we've seen before. The first of the two structures you use is actually a Frobenius algebra associated to a basis fragment. So in a certain sense, that's not very far from interacting Bialgebras. Basically, it just says that the monoid one is actually the monoid part, I guess, of the Frobenius algebra, and the comonoid. The only thing is that your comonoid doesn't have the.
Yeah, it's the wrong it's the wrong monoid.
It's not the one,
The
it's not the
comonoid's
interacting one.
Yeah, sorry. Well,
Yeah.
whichever, if you read them the other way.
Yeah, these go top to bottom. Yeah.
Sure. Then the comonoid is the comonoid part of Frobenius algebra, and the monoid is a monoid which is classical of the classical points of the Frobenius algebra. So that's not so far.